Thank you for coming tonight. I wasn't expecting many people to come to the lecture tonight, so I asked my wife and Claire to come and fill up the room. But I'm so pleased that you are all in good shape and you are here tonight as a special lecture. Roy Chadwick. He was a graduate of the University of Manchester. He graduated in what year? 1911. He did 1907, 1911. And as Roy explained, he was the designer of the Avro Lancaster and another of my favorite aeroplanes, Avro Vulcan, which still, it doesn't fly anymore, but it still goes up and down the runway in Doncaster. So if we do have enthusiasts here of the Avro Lancaster and Avro Vulcan, they can go there and see the Vulcan running up and down the runway. But the talk tonight is about graphene, and we say grappling with graphene, will it pay off? And we focus on prospects of graphene for aerospace composites. Are we familiar with graphene? Yes? Okay. And this is the graphene reinforced gown, or graduation gown of the University of Manchester. Why are you laughing? I mean, you don't see the benefits. Okay. So the purpose of the talk then is to talk about, are there any benefits there, or is it all hype? So we'll try to separate hype from science, yeah. And we'll see if the reinforced gown with graphene makes any sense. But think about it, because I'm going to ask you questions at the end of the lecture. Manchester, I have to say a few things about Manchester, the university. So it's Britain's first university of the industrial age. It's dating back to 1824, 25 Nobel Prize winners. Rutherford split the atom there. Almost 40,000 students, and we have exceeded 1 billion of annual income. We have identified research beacons: industrial biotechnology, advanced materials, energy, cancer, addressing global inequalities. But tonight we'll focus on advanced materials. And when we talk about materials, as from lightweight alloys for planes, trains, and cars to high temperature materials for jet engines and power generation, to ceramics and polymers, biomaterials, to smart textiles and composites. But again, we are going to focus a bit more and focus on polymer composites reinforced with carbon fibers. And we're going to focus on high performance carbon fiber composites with continuous carbon fibers that we can also weave into fabrics, and we can wet with resin in a multi-layered configuration to develop composite laminates where we can design for strength, stiffness, toughness. We can tailor the properties of the material system to our specific needs. Of course, what are the benefits? There are many benefits. They are super light materials. They offer us high strength and high stiffness, 3 to 6 times higher than the traditional super alloys. We can tailor the properties. We can reduce the part count substantially. They require less machining. They do not corrode in aggressive environments. But most importantly, we can embed functionality, and we'll talk about that later tonight. Where they used many sectors, from the aerospace, energy, wind energy, marine, construction, transportation. And, but they're relatively, when you compare them with metallic materials and metallic structures, they're relatively new systems. And the first commercial product appeared in 1985 when Dunlop produced the first commercial product, the carbon fiber tennis racket. And that was an expensive item to acquire. And then in 1995, we have McLaren, that they built the Formula One from carbon fiber composites. And the benefit of introducing composites into structures, it enables us to innovate. We can see here the winglet of the Airbus A350. You can make this from metallic materials, but it's going to be too heavy, too costly. This part here is 7 meters. It's a big structure. And the benefit, of course, it prevents vortices to be created and enables the aircraft to be more fuel efficient. Another successful aircraft, the Boeing 787, more than 50% of the structure is carbon fiber. And the most recent one, the 777X with the folded winglets, again 7 meters, all composite, all carbon fiber. Why do we have those folded winglets? You do aeroelasticity, fluid structure interaction. Why do we need them?
To reduce the size of hangar doors.
So it's just when the aircraft parks, it's going to parking, the wing span is too long and they fold the winglets. But that, of course, it enables the designer to give a bigger wingspan to the aircraft, which of course improves the lift, improves the performance, reduces the drag, and we don't have those curved winglets that we've seen in the Airbus A350. So how do we reduce the formation of vortices in this kind of configuration? We can discuss later. And the area, of course, where carbon fibers can be used more extensively is in unmanned aerial vehicles. And this is the unmanned, is the UCAV with the German Air Force, is the Eurohawk that probably currently flies at over our space at about 50,000 feet. We don't see it. And another smart aircraft, the F-35, it's all made from carbon fiber. And is one of the most advanced fighter jets currently in operation. And this is the complex intake duct manufactured by ATP. Roy, what's ATP?
Automated tape placement.
Automated or advanced tape placement. Yes. And it enables us to have a very complex shape that if you try to make this out of metallic materials, the F-35 will stop being smart, it's not going to be stealthy, and probably unable to take off because it's going to be too heavy. And another benefit that we get from carbon fiber composites, again here we can see that the designer of the 787 can afford to give us a bigger view of the clouds, offering us a bigger window when you compare it with the Airbus A380. Yeah, but what is the meaning of that? The bigger window, the bigger cut. Because we know the more you remove from the structure, more material you remove, the weaker the structure becomes. While here we can see the design of the 787 is very, 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 very generous, giving us more view, but removes more material. I'll ask you later why. What was the reason behind it? What does it tell us? What does it tell us? Who's going to tell me? It tells us that composites, they don't fatigue. Yeah? Or they don't fatigue as much as metallic structures. The Airbus A380, the airframe, is metallic, and metallic airframes suffer from fatigue, cracks. So we don't get cracks in composites. So does that mean then composites do not crack? Or composites do not fatigue? Of course they fatigue. Everything fatigues. But they don't fatigue as much. And here we can see how damage develops in those laminated carbon fiber constructions. This is a very simple 0-90 layup, and if we load it, say, along the L direction in tension, we're going to see that cracks start to develop These are the matrix cracks in the 90-degree ply. Those cracks, there you are, we focus on this one. At the tip of the crack now you have developed a three-dimensional stress field, very high stresses, but not high enough to break our zero fibers, but high enough to separate, to delaminate the zero layer from the 90 layer. So we have matrix cracks that they trigger delaminations at the tip of the crack. Yes, they are matrix crack induced delaminations. And then if we load it in the transverse direction as well, in addition to 90-degree cracks, we get also splits along the zero plies, which again they're going to create local delaminations at the tip of that crack. And then of course those delaminations, when they grow, they will allow the environment to penetrate into our structure. They will allow moisture to get into our composite. Moisture will plasticize the resin, and it will reduce the load carrying capability of the composite. And this is where I spend my time to develop those mathematical models that can tell us by how much the strength or the stiffness or the long-term performance of the composite will be affected by the matrix cracking, the delamination, the splitting, taking into account the environment that the composite operates. And we said earlier about that the moisture plasticizes the polymer, the resin. And you might say when the structure is loaded in tension, might not be a big problem, but when it's loaded in compression, the softer resin reduces the lateral support to the fibers that they carry the high stresses, and those fibers, they might fail in a fiber instability failure mode that we call fiber microbuckling. So although the designer has avoided macroscopic Euler buckling, his composite structure loaded in compression can still fail by fiber instability failure mode. And here we can see a composite laminate used in the F-35, or it can be in our Eurofighter, the Typhoon. Actually, this system is from the Typhoon. It's a typical hole for rivets, hole diameter about 6 millimeters. The skin is about 3 millimeters thick. How many plies? It's a carbon epoxy system, autoclaved, manufactured, so it's about is 24 plies. 24 plies. Ply thickness 0.125. And it's been loaded at about 85% of its ultimate static strength. We don't see any damage. We might see probably, I don't know, some kind of few micro cracks there, but probably they were introduced during the drilling process of the hole. Again, if the operator that drills the holes is not careful, and I've been to factories where I have watched the technical people drilling holes, and they create local delaminations, and then the guy behind them with a pot of resin comes around and fills the gaps up with resin, and I tell them, sorry mate, it's not going to work. Already the laminate has been delaminated. And this is what's inside. Extensive amount of damage in the form of the splits that we've seen earlier, the off-axis ply cracks in the 45 plies, and those delaminations that they start and they follow the path of the crack. And if someone has a well-trained eye, this is an X-ray CT, X-ray computed tomography. We're going to see something is happening there. And what is happening there is that the fibers, the actual fibers that they carry the compressive load, have lost the lateral support, so the neighboring layers have delaminated, they don't support the zero plies anymore, and the fibers buckle at the microscopic level. That's the crack, and this is the fiber microbuckling. This is the axis that we load the plate, and this is how they break. Fiber diameter is about 5 micrometers. So this length here is about 10 fiber diameters. And when that crack reaches a critical length of about 2.5, 3 millimeters, depends very much on the layup and the stacking sequence, then it propagates catastrophically and you cannot arrest the crack. So the challenge that we have is to identify non-destructively that damage that happens inside, identify what's the critical length, and predict or estimate when that laminate is going to ultimately fail. And here is one of my models that takes into account initial imperfections, the properties of the fiber volume fraction, and try to calculate, by solving this fourth order differential equation, the critical stress at which fiber instability will take place, accounting for interlaminar shear stresses that they develop at the free edge. If you had a metallic plate, the free edge is stress-free. You have no stresses. In the composite, you have a three-dimensional stress field that this beast here, this component of interlaminar shear, will destabilize further the wavy fibers, and they will trigger microbuckling at a lower applied compressive load. And here, this is the properties, the shear modulus of the polymer that supports the fibers. And it's not a constant value, but it varies with the applied load. So it takes into account the entire nonlinear response of your polymer. And that was the invisible damage that we cannot see and will struggle to identify non-destructively, while this one, we don't need NDT or SHM. We can see that there is big damage. There is big damage. And this one also has suffered lots of big damage. Do we recognize that aircraft? It is. But then here's a graduate from Queen Mary College, so say. And what's special with this? What does it tell us? It tells us that this aircraft can suffer lots of damage, yeah, but can still perform its functionality. It didn't fail. It didn't collapse. It didn't, they didn't manage to destroy it, or didn't fail catastrophically. The pilot managed to land the aircraft, yeah. So here then, the challenge is how we can design and build structures that they can still perform well in the presence of damage. Of course, ideally, we would like to make first damage resistant, but once damage does occur, we want them to be damage tolerant, so they can tolerate the damage. Okay, so that's the task we have, how we can make the structures damage resistant. And then eventually when damage does occur, because as we said, everything gets damaged. But once it gets damaged, can it still perform its functionality? Here is another type of damage. Most of that damage happens accidentally. People, they walk along the aircraft wing of the Airbus A350 and they drop their tool and they damage it. And then the challenge, of course, is can we fix it? Can we repair it? Of course, in the lab, you can repair it, you can recover the shape, you can recover the strength and the stiffness, but also you have to recover what is important in aeroelasticity.
Rigidity.
The rigidity, yes, but also you can make it too rigid, yeah? You can make it too stiff, and then the loads will redirect themselves and follow the path of the structure that it's locally weaker. So we have to make sure that we don't make it over stiff, we don't make it over rigid. Yeah? So it's not only the static behavior that we have to worry about it, but also the dynamic behavior. So when we repair, say, the vertical fin, we have to recapture not just stiffness and strength, but also the aeroelastic behavior, which is a dynamic aspect. And then the other type of damage you can get is blast. You put a few grams of an explosive inside the aircraft. In this case, we were very lucky because it did happen at very low height, so the pilot managed to land the aircraft, but if it does happen at 40,000 feet, you cannot rescue the aircraft. And then the task we have as designers is how to, in those critical areas so where you suspect things can go wrong, to develop a material system that can dissipate the blast energy in a way that you don't get perforation. You get damage, and in the formation of damage, you absorb that blast energy without getting perforation. And one way of achieving this is by moving into hybridization, introducing hybrid laminate constructions. And here we can see Achilles, Prince Achilles. Have you been to Hyde Park in London? Yes. If you go there next time and you visit the Royal Aeronautical Society, just across you will visit Hyde Park, and you're going to see Prince Achilles, a big statue, yeah? And he is holding his shield. And his shield is a composite laminated structure similar in design to modern aircraft construction, where we use glare for the upper part of the body of the Airbus A350. And glare is a combination of metallic aluminum layers mixed with glass fiber reinforced plastic. And there the designer is trying to optimize not only strength and stiffness, but optimize toughness. Where in the case of the blast loading that we've seen earlier, the blast energy will be absorbed in the form of matrix cracking, extensive delamination. So in this case, it is damaged, but they behave now like energy sinks, where you dissipate and absorb energy and prevent perforation. So if we go back to Prince Achilles, we're going to see that his shield was made from 2 outer layers of bronze, 2 inner laminae of tin, and 1 central lamina of pure gold. I don't know if you can afford gold these days. But the purpose of each layer, it was related to strength, stiffness, toughness. So when the spear hits the shield, you don't perforate, and then you don't shatter. You don't break in a brittle manner the shield. So, because you can have something which is very stiff and very strong, but then under impact, it shatters like glass. Well, in this case, by optimizing and tailoring, you can achieve strength, stiffness, and optimum toughness. And of course, you have to perform numerical simulations to identify what's the best combination of different layers in order to prevent the perforation of your skin of your aircraft. And of course, you have to take into account not only the blast, but also that your fuselage now is pressurized. And this is a combination of aluminum layers, which you can see extensive plastic deformation, but not perforation. And you can see extensive cracking in the composite, but overall the whole laminate has been kept without the hole. Another way of improving on toughness is hybridization, but this time we produce not at the layer level, but at the fiber level, where the designer mixes glass fibers that they provide you stiffness and strength, and protects those glass fibers with low-cost thermoplastic fibers, in this case polypropylene, and in the case or in the event of impact, this is during the impact event and the extent of impact damage you get. And then if you heat them up after heating the laminate, those thermoplastic fibers melt. They melt and they fill up those delaminations and cracks. So you recover the strength and stiffness of the laminate. And you also improve the post-failure compressive behavior of the composite. So we have hybridization at the ply level, hybridization at the fiber level, Or another way of preventing brittle fractures and brittle failures is by reinforcing our composite through the thickness. So you prevent the composite to delaminate at relatively low applied loads. And the effect of the through thickness reinforcement, it's visible under an impact event. So on the left-hand side, we have a two-dimensional woven fabric with no through thickness reinforcement. And on the right-hand side, we have a three-dimensional woven loaded under the same impact conditions. But what is missing from here is we don't get that extensive delamination and extensive matrix cracking. And the idea here is to achieve a composite system where you remove material, you damage material without affecting the load carrying capability of the composite. And what we plot here, we plot the tensile stress versus the actual strain for the undamaged material and the damaged one. Because usually when you have a piece of material and you remove a hole, you make a hole, you remove material, it becomes much weaker. Well, here we see we have removed material, but the stress strain response has not been affected. And this is what we call, if we go back to the A10 aircraft, what do you call it?
The wafer.
Exactly, the wild pig. We can see that you do have perforations, you do have holes, you have removed material, but the structure is damage tolerant. It doesn't feel the pain. Yeah? It doesn't feel the pain. So it becomes not insensitive. It becomes damage tolerant. So we have spoken about hybridization at the pline level, hybridization at the fiber level, and we introduced the through thickness fiber reinforcement that makes our structure to tolerate damage. But the talk was about graphene, wasn't it? So let's see what graphene can do. And here we are, we have our carbon fiber, we have the woven fabric, we have our resin, but this time we put some graphene there. We put some graphene. And what kind of expectations we have from that graphene? Improve our resin, make our resin harder to crack, maybe make our laminate more difficult to delaminate. Let's see. Maybe I can give you also something that you can take home with you. Yeah. You can have a white part, and you can have a black part. And you can circulate, and later on, at the end of the lecture, you can have also your own with and without. So the white part is without graphene, and the black part is with 1% graphene, or less than 1%, probably 0.5. And that graphene, what it does, it improves the impact performance, the fatigue resistance. It gives us better wear resistance, but also it can sense. So when the aircraft mechanic drops the spanner on the composite wing of the Airbus A350, if you were the mechanic, would you report the incident?
Yes.
She wouldn't. But in his case, she would, because she's a good guy. But the bad guy wouldn't report it because he will get into trouble with his line manager. Because the line manager will say, now we have to fix it. We have to do the inspection. We have to find out if there is damage inside that we cannot actually see with naked eye. So we have to stop the flight to inspect the aircraft. But if you have sensors inside that skin. You don't need to ask the guy who dropped the spanner. It will be recorded automatically and will be reported automatically. But of course, where graphene really can make a huge benefit is on electrical functionality, environment protection as well, high temperature tolerance. We can improve also the coefficient of thermal conductivity. We can make the polymer to be thermally conductive. Why do we need that? We'll see later on. But first of all, let's say, what is graphene? Are we familiar with graphene, all of us? Do we know graphene? Almost? Yes, yes. So it's a two-dimensional material. Why do we call it two-dimensional? Because it's super thin. How thick is it? 1 atom. Whew. 1 atom thick. So, and we have different types, of course, of carbon-based materials. The 0D bucket balls. This is 0D, zero dimension. What is it, zero dimension? It's a little dot, isn't it? It's a dot. 1D is long, it's carbon nanotubes, single wall or multi-wall carbon nanotubes. And of course, this is the traditional 3D graphite. And of course, from the 3D graphite, we can produce the graphene, and we'll see later on how we can do that. And some graphene superlatives that you can find on magazines, newspapers, and people in Manchester talking about the thinnest imaginable material, the strongest, the stiffest, the most stretchable material, the highest current density at room temperature, 1,000,000 times of those in copper. It conducts electricity, heat, and so on and so forth. It's a lengthy list of good things. But we have to make it first. How do you make graphene? One way is top-down, where production is by removing elements from a large starting material. So you have a large block of graphite, and with your little hammer you start removing the graphene. So you have the top-down method and you have a bottom-up, where you structure your graphene into the material atom by atom. So we can do the electrochemical exfoliation. This is a method developed at the University of Manchester. Gram-scale production of graphene using electrochemical exfoliation. The Nobel laureates, of course, they used the Scotch tape exfoliation technique. They took sellotape and they started removing. And luckily enough, they were successful and they received the Nobel for Physics in 2010. So you get hundreds of graphene flakes, a few layers thick, but they come with variable sizes and variable thicknesses. And that might affect, of course, performance. And the other way is with chemical vapor deposition, where you have a substrate of copper, annealed copper at 1,000 degrees Celsius, and you grow graphene layer, atom by atom, at 1,000 C. And it takes about 1 second for that graphene to start growing on the copper substrate. And of course, you have to scale up the production method. And then once you have produced your graphene successfully, you have to characterize it. You have to measure those properties. And here you are, you take that flake, this is the flake of graphene, and you use the atomic force microscope, and you perform a 3-point bending, yeah? And you extract the stress-strain response, and you can measure the Young's modulus that comes out as 1 terapascal, and the ultimate strength of 130 gigapascals. How is that? Whew, 130 gigapascals. What do you understand by this surface area? 1 gram of graphene is 2,630 square meters. What is the physical meaning of that? Who's going to give me a good example? Some of the younger generation. Yes? What do you understand by that? You look at this. Professor Thurai says to you, surface area is 1 gram is 2,630 square meters. It is, exactly. So with 2 grams, you can cover the whole stadium of Manchester United with graphene. And so our players can play on graphene field. You know. The park, we can convert the park of Man United with 2 grams of graphene. And it's transparent to light. Oh, I'll circulate you this. It's a black bin back. No, it's not. It's not. It's been reinforced with 0.1% graphene. It's a cheap polymer reinforced with graphene, which of course it means that you can produce coatings. Yeah, you can produce many things. You can produce films. Plastic films with special super properties. We'll see what kind of applications they can have later on. So you characterize it, and then you measure electrical properties, and we can see conductivity. Conductivity increases by 12 orders of magnitude. So you have a polymer which is not electrically conductive, and suddenly, with a small amount of graphene, it conducts electricity. And then we've seen at the beginning of the lecture that we can build composite systems layer by layer. But with graphene, it enables us to build materials atom by atom. And then some of those layers, they can be the sensor, some others they can be the solar cell where you store energy. And that energy runs the whole system with the amplifier, and the interconnects all these layers, and some of these other layers that can provide us with the reinforcement. They can give us the stiffness, they can give us the strength. So instead of building them layer by layer, we can go down to atom by atom. And each layer can have different functionality. And then if you start thinking of applications, then it's optoelectronics, high-frequency electronics, sensors, flexible electronics, batteries, and of course the traditional composites and membranes and lightweight construction for high-performance applications. And to one of those applications now, we can go back. You remember when we did the hybridization at the fiber level, where we used the thermoplastic fibers to protect the brittle glass fibers, and they give us the high strength and the high stiffness. And we said by heating up the material, the polymer, the thermoplastic fibers will melt and will fill up the cracks. But if your polymer is not thermally conductive, you expose it to very high temperatures, so you might cause damage. But if your polymer is modified with graphene, which improves the thermal conductivity, it becomes much easier then, and at lower temperatures, to melt those thermoplastic fibers and repair your composite structure. Another application is filters. Graphene filter covered in tiny holes. I don't know if you remember the microstructure of the graphene. It did have holes. And those tiny holes, they're big enough to let water through, but small enough to capture the salt. So the next war in the Middle East is going to be not about oil, but about water. And if we can provide solution, then we're in good business, aren't we? So start investing on graphene filters. This one appeared the other day. It was, Claire, have you read the article?
Yes, the
AIAA. And it didn't even mention that this is the magma, is the is the flying platform of the University of Manchester that we use it to display technologies developed by our researchers. Just it was saying it was BAE Systems, but for Americans, BAE Systems, it means nothing. They say some kind of American aerospace company. Yeah? But it's not BAE Systems. BAE Systems is one of the sponsors. It was developed by the university, Bill Crowther. You know Professor Bill Crowther? Yeah? He was behind it with his team, and of course many other people that contributed. This is the morphine that we developed also, the morphine trailing edge. And here, of course, about graphene, the printed graphene antenna. So a graphene antenna could give us wireless terabit uploads in 1 second. Terabit. Another incredible use for graphene is high-power graphene supercapacitors. So you can fly your UAV forever instead of 5 minutes or 10 minutes until your battery runs out. Aha! And we relate this back to what? What was the first slide of my talk today?
The gowns.
The gowns, that's it. Thank you so much. These guys, whew, are you fast asleep here? It's the gowns. So this is the first wave of conductive fabrics that will carry heat or electricity around your body, but without any power source. So here, the jacket transfers heat from the hot part of the body to the cold part of the body. Yeah? So you don't need gloves. That's for Claire. Always she feels cold, you know. She can get her first. I mean, at the moment, the jacket is 525 pounds. But you see, you're going to say, you see, I have a graphene reinforced jacket. But we're here tonight to talk about airplanes anyway, and we've seen those composite airframes, carbon fiber airframes. How do you protect them from lightning strike? Because those polymers, they're not electrically conductive. How do we solve the problem at the moment with the A350 and the 787? What do they do? Nick, what do they do? Conductive mesh, yes, copper, but copper does what? It's very heavy. What's the density of copper? He doesn't know, but it's heavy. Yeah, it's heavy. So we remove the metals, we replace them with composites, and then we put metal on top in order to make them conductive. So the idea is how we can cover the Airbus A350 probably with a conductive graphene modified polymer to remove that copper mesh. Where's my beam back? Yeah, you see there you are. Yeah, you can make them more conductive. Let me see what's here now, what's happening. Let me play the video clip. What's happening there? What am I trying to do? So we have the polymer reinforced with graphene particles. In this case, the graphene particles, they are perfectly uniformly distributed. You have no clusters, you cannot see them. All right? You cannot see them. That was the purpose of physics hour, yeah? You cannot see them. But there, what I have done, I want those particles to be connected. I'm developing networks in order to allow the current from the lightning strike to go through my polymer very quickly. Because if they are nicely uniformly distributed with gaps in between, the electrons, they're not going to flow, are they? Well, there, they will. So you create the polymer reinforced with graphene platelets where the platelets are connected. And they allow the current to flow through. And what was the first commercial product with carbon fiber? It was 85. It was a tennis racket. Here is 2014. It's the head graphene tennis racket with one flake of graphene somewhere there. But still people is prepared to pay big money for graphene modified tennis racket. Yeah?
In case it gets struck by lightning.
In case, absolutely. Multifunctionality, we call it.
Play the ring.
Golfers, yes. And here,
Formula 1.
Formula 1 car, it's the Lotus, and here is our Formula 1 driver. Dame Nancy is the president of the university, the Nobel laureate guys there. And here is your broken smartphone, yeah? But can you imagine if we have something that is plastic touch screen that uses graphene as a conductor? So then it will never break, isn't it? So that's not a good application there. So let's go through very quickly some of today's challenges that we are facing with composites. Increased supply of raw materials. We need to have access to raw materials. We reduce material cost, reduce finished part cost, processing, manufacturing. Drilling, of course, is an aspect that we very briefly spoke about. Joints, bonded joints, bolted joints, riveted joints. Machining, drilling, assembly. NDT, we need to develop reliable, non-destructive test techniques and real-time structural health monitoring to observe those cracks, micro cracks, how they initiate, how they grow, how they interact and create delaminations, and eventually they introduce fiber breakages, fiber instabilities, and catastrophic failures. Material supply chain, where your materials come from. Can you still have access? Who controls the flow of those raw materials? And of course, when we talk about graphene, how do we know that this is graphene? Because there are so many derivatives of graphene, that they don't have those super properties that we spoke about, the terapascal stiffness or the 130 gigapascal strength. Yeah? Because if it's not pure graphene, and it's graphite, you don't get those super properties, or reduced graphene oxide, or graphite oxide. So there are many derivatives. So we need to develop test methods. We need to develop ways of identifying the purity of the material that we are producing. Otherwise, we don't get those super properties, the electrical, the thermal, the mechanical, the toughness that we spoke earlier. And like all carbons, manufacturing route determines the properties and cost. Currently, the cost of graphene has dropped dramatically. 1 kilogram of graphene is about, no? Yeah? No? 250 pounds. But 1 kilogram is a lot, because if you with 1 gram, you can cover the whole of Man United. You can imagine what you can do with 1 kilogram, yeah? But the thing is, how do you know that it's graphene? Yeah? You can go on Google, you can order your 1 kilogram of graphene, you pay your 250 pounds, the graphene arrives, how do you know it's graphene? And of course, the other thing is modeling aspect. Because we need to characterize them not by breaking, but by performing the analysis first. At the atomic level, at the nano level, the micro scale level, the macro scale, and the structural level. So we need to have those mathematical models that will enable us to estimate the long performance, or to design and optimize the strength, the stiffness, the electrical conductivity. And then we talk about industry 4.0. Here we are, cyber physical systems that will enable us to do all that modeling in one go. automation and data exchange in manufacturing. It includes cyber-physical systems, the Internet of Things that you have heard of, and cloud computing. But in order to run all this, what do we need to have? We need to have, at the moment we're talking and struggling to introduce 5G, but our competitors are moving on and they talk about 6G. 6G. What does it mean, 6G? In terabits, in milliseconds. So you can download the whole of Netflix library in seconds. Of course, the automotive industry, they use extensively robotics, and introducing composites into the automotive, 10% mass savings translates into 6 to 7% of fuel savings. So that's another good reason to transfer technology from aerospace applications to all other means of transportation. And while until now the aircraft industry is all handmade, here we can see the introduction of robots doing the airframe of the Airbus A350. So this is, it opened just before Christmas. It's the highly automated and digitally connected A320 fuselage assembly line in Hamburg. So it's all computer controlled. And the future, what is the future? The future is the blended wing body. It's not a new concept, but it's a new concept for the civil aviation. Yeah? We have already blended wing body military aircraft, but we don't have anything to fly passengers around. We don't have anything that can carry 450 to 950 passengers. At 15 kilometers, 15,000 meters of range and 10,000 meters, so it's about what? Yeah. And it's not only schematic, this is the small-scale demonstrator that flew recently by Airbus at the air show in Singapore. So as you can see, we can see that the aircraft manufacturers of jet airliners, seriously, they are thinking of building the next generation of aircraft carriers in that form to reduce fuel consumption, to make it more efficient. And that is enabled only by composites. Maverick, they call it. What is Maverick? What's Maverick? What does it stand for? This model is 2 meters long by 3.2 meters wide. Maverick. Claire? Maverick? Oh, come on. Model, aircraft for verification and evaluation of robust and innovative control. And why do we need blended wing body? Many drivers for the future design is greener, quieter, safer. The current design is more than 70 years old. It's the cigar type. You have a cigar and you attach to wings. The body doesn't create lift. Yeah? So the whole thing now, the fuselage generates lift. It reduces the drag. It reduces emissions. You need 2 engines instead of 4 engines. But of course, you have many challenges. And the main one is that aerospace and aircraft design is very multidisciplinary, integrated design. You cannot rely on one designer and say, I'm going to design and build that next generation of aircraft. You have to bring teams from different disciplines. Trim and stability, takeoff, cruise and landing, manufacturing, public acceptance, evacuation, so many parameters to consider. And that's why you need those multidisciplinary teams to come together and get together and exchange ideas, interact, and build the next generation of aircraft. Thank you so much.
Thank you.